Hi, this is Mick West on Metabunk.org, and we're having a look at the Metabunk Refraction Simulator. I wrote this refraction simulator over the last, I don't know, several months, based on a view of Toronto. This is Toronto here, and this is the CN Tower, and this white thing here next to it is the Rogers Centre. And this view is from Fort Niagara, which is across the lake on the other side of the Lake Ontario. And from that position, theoretically, you shouldn't be able to see the Rogers Centre because it should be hidden behind the curve. But you can see it because of the refraction lifting it up beyond the curve. And this confuses people. So I wrote this refraction simulator to explain what's going on, or to demonstrate what's going on. First of all, let me just show you real quick what this view should look like without refraction. There's a checkbox over here on the left where you can turn refraction off. So if I turn it off, this is what you would expect to see if there was no atmospheric refraction. All these buildings down here are hidden, but when there is refraction, it pops into view. Now, of course, refraction isn't a constant, so I had to make it editable. And over here on the upper left-hand side is the temperature profile. The temperature on Celsius is along the bottom, and the height above the water level in feet is on the left. I'm kind of mixing my metric and imperial units. And this is a curve editor, and this curve represents what the temperature is at a particular altitude. Say at 60 feet here, it's 15.5 degrees, and I can grab that and I can move it around, and you can see this has a quite dramatic effect on what you actually see. This curve editor you control by moving these points around. You can change the shape of the curve with the green, and you can change the actual data points by moving the black ones around. You can add new points if you want to make a more complicated curve by just clicking in any empty space, and it will make new points. You can delete points by left clicking, and that will remove a point. So you can create all kinds of interesting effects that are things that you can see in real life. You can see, for example, you can see big compression near the horizon here, and you can see the Rogers Centre being lifted up. If you have the water temperature or the lower down temperature a lot hotter than the upper temperature, you will create a kind of mirage effect where you get this mirroring, which kind of looks like what you see sometimes on a hot road. When the road is very hot compared to the air, you get this reflection, this kind of total reflection from refraction. So you can mess around with this temperature curve and see the various effects. Now, of course, it would be a bit boring if we just did Toronto, so I made it very, very configurable, and you can actually look at lots of different places in the world and lots of different situations. You can even set up your own. So let's just go through a few things right now. I'm going to look at the controls over here. I'm just going to reset this. If you click on preset link, it will load the last preset that you had. The viewer height here is in feet. You can just move this up and down. If you let go, it will pop back to the middle and kind of reset, so you have to keep dragging it, and you can get higher and higher. As you would expect, as you get higher, you can see more and more. I'm just going to reset that again. If you click on refraction on and off, it's fairly straightforward. Standard refraction just makes the temperature profile be a straight line, just getting colder as you get higher, which it's kind of like the standard atmosphere. So it gives you like essentially an average refraction. If you look at my curve calculator, this amount of refraction is what you're seeing when I'm calculating how much should be visible with standard refraction. I can turn refraction on and off. You can see this is the effect of standard refraction. And if you turn standard off, you get the curve back again, and you can edit the curve, and you can get the more interesting effects from refraction. Let's see this. Click on eye level, it will show you where your eye level is, which is like 0 degrees basically, relative to the local vertical. And you see in this situation, the horizon is below eye level. And if we turn off refraction, this is like it's essentially no atmosphere. You can see it's below there. And with standard refraction turned on, it's below. And with this, you can see that the reflection that we're getting in situations like this is actually happening below eye level. All right, I'm going to reset things again because I'm messing up. Viewer offset is just a simple thing. You can move things left and right. It's kind of useful if you want to set up a nice scene, like say you wanted to do this. So you could see this. Now what this window actually is, I should probably explain that. This window is essentially the side view. It's greatly compressed left to right. This is showing you the curve of the Earth. This is where your camera is, and this is where the target is. So this represents the full height of the target image. And you can see where this yellow line is here, and where the yellow line is there, like it's touching the top of the CN tower, and also the top of those clouds, which is where the top of the image is. The red and the blue lines, the red just represent lines that are going up, the blue represent lines that are going down from your point of view. So you can see, if we turn on eye level, you can see that right here, between the red and the blue, is where your eye level is. If you turn off refraction, you can see it's just going to be perfectly straight there, with the red going up and the blue lines going down. And this is more apparent if you increase the viewer height to be a much higher altitude. All right, so reset again. The next thing to look at is the viewer vertical FOV, which is perhaps a little of a long-winded way of putting things, but this is basically the field of view vertically for the entire screen. And here it's set to 1.5 degrees. This is essentially the zoom on a camera, but I'm expressing it in terms of field of view. I should perhaps also put the millimeter equivalent zoom there. A P900, Nikon P900 is about 0.6 vertically, so this would be the maximum zoom of a Nikon P900 for this particular scene. Now let's see, viewer tilt. You can just tilt the scene up and down. It's just so you can get it into a good position. It doesn't really change what it actually looks like. Then here there's a field called, well, let's see, image files. This allows you to put in your own image files. You could go to Google Images, and I could do something like type in Tower Bridge, find a nice straight-on picture of Tower Bridge. Here we go. And let's see, I can do a copy image address and stick this in here. I'm not sure if this is going to work or not. Bam, there you go. So you'd have to actually, once you've put in a target file, then you have to put in the target height. It's 2000 here, I think. Tower Bridge is probably more like 800 feet or something like that, and probably less than that. Let's say 500 feet. Nah, it's probably not even that, or is it like 300 feet? Anyway, so you would have to look that up. Oop, you can see it's hidden behind the horizon now. Now, target distance is the distance to that target, so I can bring it a little bit closer, give it a bit more realistic looking. This is in miles, target height is in feet. I kind of mix the units a little bit, sorry about that. Next two things are multiple. You can actually make multiple versions of an image. So if I put in 4 and then put in, say, like 3,000, this is in feet, it makes 4 copies of this particular image. You can actually see them though, because they're all behind one another. I think if I change the offset, you might be able to see how they are behind each other. Let's change this gap to 10,000. There you go. You can see them going off into the distance. So you can set it up with multiple images. This Shuri N lines is just the density of lines here. It's not very important. Wavelength is the wavelength of light that I assume for the calculations. If you want, you could try changing it to something else, like, for example, infrared light is going to be around 1500 nanometers. So you can change that. You can see it makes a very, very slight difference to what you're actually seeing. Now, probably the more interesting thing here is all the different presets. Like, for example, let's see, Catalina from Santa Monica. This is kind of a classic view. This is the view from 6 feet on the beach, Santa Monica, and it's based on photographs that I took. Well, when I visited a few years ago, you get this very nice hidden part of Catalina. Now, I have a flat Earth view. If you click on flat Earth, it'll show you what it would look like if the Earth is flat. And this is what it should look like from 6 feet if the Earth is flat. This is actually with refraction. turn refraction off, it will actually look like that. You see there's a huge amount of Catalina Island down here. This is Twin Harbors down here, just going to behind this thing here. But what you actually see, and what you see in my photographs, is the non-flat Earth view, the view with refraction. Let's turn on standard refraction. This is what you'll expect if it's just a flat curve. This is what you actually see from Santa Monica Beach, which pretty much by itself just proves that the ocean is curved. Because there's a very, very big difference between that and this. Anyway, that aside, I'm explaining how to use it, not what it's proving. Chicago, view of Chicago. And let's see, look at a more interesting one, the Bedford level experiments. Here is the classic Bedford level. This is a 6-mile stretch of canal. I'm obviously showing it as open ocean, but you can think of it as it being a canal, obviously. 6 miles away is this bridge. Now we had to get the field of view all the way down to 0.1 here so we can zoom in, so that's a very powerful zoom. P900 view would be more like this in the full frame. So you'd still be able to see it. You probably want to use the digital zoom to see it all the way. So we've got two things here. We have this target, which is set halfway along, and we've got this guy in a boat. And we've got our viewer height set at 14 feet, which is about the height of this target itself in the middle. And it's the height of this bridge itself. And this is a classic experiment that's done. It's a little hard to visualize perhaps, but if it was a flat Earth, and I can actually show that, let's turn off refraction, go to flat Earth view, then this one here is actually at the top of the bridge. This one here is quite a bit below because you're looking straight at it. But if we go to the non-flat Earth view, then this one is above the top of the bridge, completely different. And this kind of is a very good demonstration. If someone could actually repeat this, it would be great. It's a good demonstration of the curve of the Earth. And you can play around with this. An interesting thing to do is you go to the different version of this, the Bedford level boat. This has the viewer height set at 4 feet. And this guy in the boat, you can actually, let's see, this field here, target to edit, shows the different targets here. So there's a 2-disc target, the man in the boat and the bridge. We take the man in the boat one, we can change his distance, so we can bring him closer. So this is him just a mile away. And you can see he keeps going further and further and further away, but he doesn't actually disappear. Even though he gets all the way to the bridge over there, you can see him. Now this was a classic experiment that was done in the 1800s, and it was thought by the guy who did it, Samuel Rowbotham, that it demonstrated that the Earth was flat because he could see this guy all the way down to the bridge when he should actually have disappeared. If I turn refraction off, you can see what you would expect to see, which is the guy disappearing smoothly over the horizon and be completely invisible at about 5 miles. But he didn't see that, he saw it visible the whole way because there was atmospheric refraction. So he was mistakenly assuming that the Earth was in fact flat, because he would have been vastly distorted and you probably wouldn't be able to see him. Now another thing that brings up is low-level humidity. We can actually edit the humidity. I set it at 50% by default, but we can edit it using a curve, using the same curve editor type thing as we do for temperature. And it's actually interesting for something like this. The humidity has a quite large effect on small things that are very close to the horizon. It doesn't have much of an effect for large scenes, but for something like this it can have quite a dramatic effect. But I'm not sure how realistic this curve is, but I'm letting people edit it and perhaps they'll figure out what the actual limits to refraction should be. Another classic, a modern classic, is Lake Pontchartrain. I call these pylons, in England we call electrical transmission towers pylons. And this uses the multiple thing here. We got these targets, electrical towers and boats. So this one here has a multiple of 80 targets with a gap of 979 feet in between each one. And I think that this is just the first target here. First target distance is in miles and the subsequent gaps are in feet. Again, I apologize for mixing the units. Then this is a boat, which I just stuck in just to give you something else to look at. You can change the distance to that one. This is a classic because you can see the curve quite clearly. You can move around from left to right as if you're moving along the freeway. So you can take this. And interesting things we can do here is that we can actually mess around with the temperature gradient and actually kind of flatten out the curve by moving it this way. And we can actually raise it up. And there's a photograph that shows this kind of condition where you have very, very cold water relative to the air. It can actually make the curve of refraction go around the Earth. That's, very similar curve to the actual Earth itself. And so it actually makes it look flat, which is kind of annoying when you want to demonstrate these things. But it only really works for things that are fairly close to the horizon, because you need this kind of steep temperature gradient, which you only really get when it's close to water. Things like distant mountains, it doesn't really work. Other interesting things. This is a simulation of a Fata Morgana, which is caused by a steep inversion. At this point, 100 feet up, the temperature is going down normally, then it suddenly increases with a warmer layer, just 2.5 degrees. But that is enough to create these quite dramatic effects. By moving it around, you can see how quickly it can change with just a very small amount of variation in these values. This is something I actually observed from Santa Monica, and I was going to duplicate the same thing. I think it kind of covers a lot of things. There's one flag that's distant laser spot 3 feet above the water level. And what's interesting is you can see the laser, but you have no idea what's really going on. That's because I have this night flag turned on. If you turn off the night flag, you can see you've got this ridiculous amount of refraction, and you just happen to be able to see this laser just kind of poking through it. If I zoom out a bit, you can see more what's going on here. The laser's down here somewhere, and if I move this around, you can see it's just randomly that it happened to bump into view. There it is again. The laser down here. But this just shows how difficult it is to see what's going on when you do experiments at night, which is exactly why I did this particular configuration. I think I've pretty much covered everything. There's a bunch of different examples in there that you can look at. This boat is actually in my book, Escaping the Rabbit Hole, and you can do things like select the boat, sailboat here, and move it closer or further away, and you'll see it disappear. This is a situation I just have a fairly boring temperature curve. You can actually make it more dramatic. Colder water is what normally happens, and see what happens. Just mess around with it, see what effect cooling things down has. You can see it there for longer, and you see more compression. And I think I pretty much covered everything. Well, it covers how to use it. Now, you might want to set up your own things. You can add a new target, and it just basically duplicates the pre-existing target. I'm going to expand this later so you can select which image to use. It doesn't really let you do that right now. And you can do various multiples of things. If you've got a nice setup, say you think, I want to share this with people, this particular scene, you can click on permalink, and it will give you a link on the top here, a very long link, but you can still just take it and post it. You can post it in a forum post. It usually works on YouTube or on Facebook or even Twitter. And this will take them directly to this scene. If you just reload that now, it takes you to the exact same scene, which is quite handy for sharing it. There's another button here, Export, which will create a text version of the data, which I can then stick into my code. So if you have a nice setup, then I can take that and put it into the code as a preset. This link here will take you to the discussion thread, and I think that is pretty much everything. So if you've got any suggestions, I will be happy to add things to this. A couple of things I didn't say. You can turn this side view on and off. You can also make it turn off the gradient so you can see the lines a bit easier. Ignore this debug thing, it's meaningless, it's just a test thing for me. Yeah, so if you have any suggestions, just let me know and I will be happy to add it given time over the next weeks and months, because I'm actually quite enjoying messing around with it and using it to explain things to people. See ya.